Okay, in this video I'm going to talk about special types of matrices. So we are going to check some special types that might have some role in helping us in solving different types of systems using matrices. Okay, so let's see the first type or the first version that we are having here. So it is, we call it the orthogonal matrices. Orthogonal matrices. The definition of orthogonal matrices is going to be like this: an n by n matrix, so it should be n by n, is orthogonal if its transpose, take care of this, is its inverse. Means that the transpose of the matrix is its inverse. So if they are the same, then we call that this matrix is orthogonal. This matrix is orthogonal. Okay. And when we are in this case, when we are saying that A minus 1, or the inverse of the matrix, equals to its transpose, okay, in this event, of course, this is logic. A dot A transpose equals to A transpose dot A. It's like commutative, and it equals the identity matrix at the end, IN. Okay, so it equals to the identity matrix. Okay, so the main idea of the orthogonal matrix, or the main definition, that we are having A, the inverse, equals to the transpose. Okay. For example, it is routine to check that. You can check this by yourself. Check that this matrix, which is composing of 0, 1, 0, and 1 over the radical of 5, 0, 2 radical of 5, and 2 over radical of 5, 0, minus 1 times radical of 5. We can check this to be orthogonal. Okay, check it. Okay, check it. Try to find the inverse of the matrix and find the transpose of the matrix, and you are going to find them equal to one another. Equal to one another. Okay, just multiply this matrix by its transpose to obtain the identity matrix I3. You are going to obtain I3. So the simplest thing is you're going to multiply this by its its transpose, as we said here. It is going to give you IN. Okay, IN. So if we are talking about A, for example, 3 by 3, then IN is going to be identity matrix. That is going to have also like the all of diagonal zeros, and these are ones, and this is of course I3, because the dimension of the matrix is 3 by 3. Okay, because A transpose, the transpose of the transpose equal A, and this is right because we said that A, okay, A transpose of it would equal to A. A matrix is orthogonal exactly when its transpose is orthogonal, and this is right and logic also, right? Because the transpose of the matrix, we are assuming here, if A is orthogonal, okay, then we are telling that A transpose is also orthogonal. Okay, this is what we are telling you in this sentence. Okay, they are going to be orthogonal too. The transpose of the matrix is going to be orthogonal too. It is also easy to verify that an orthogonal matrix must have determinant 1 or minus 1. Let's clean here the things. So we are telling that the determinant of the matrix, okay, of the orthogonal matrix, okay, is going to equal 1 or minus 1. Okay, this is also another property for the orthogonal matrix, okay, that the determinant is 1 or minus 1. This is going to, greatly simplify all the calculation for many cases, right? So the orthogonal matrix is really important property, or considered to be a special case that is going to play a good role if there are some matrix operations that needs calculation of the determinant, right? Okay, now let's go and put the theory or the theorem so that we can like remember it always. If A is orthogonal, then the determinant of this A is 1 or minus 1, if we say that it is orthogonal. Okay, the issue here is the orthogonality. Okay, the issue is the orthogonality. Okay, and the proof is very easy actually, because a matrix and its transpose have the same determinant, right? The matrix and its transpose, they are both having the same determinant, right? In, for example. Then this in, the determinant of in, what is the determinant of in? Okay. It equals to what? Exactly 1. And it equals to this in we mentioned before, that as we know, A times A minus 1, or the inverse, equal to the identity matrix. Okay, then we're going to say now, because we are orthogonal, so it is going to be A times A transpose, right here, equal to here. This is from the orthogonal matrix definition. Then we're going to end up with A, or the determinant of A times the determinant of the transpose of A equals to the determinant of A squared. Okay. What can like make this to be true, which is 1, for example, or plus 1, minus 1 or plus 1. They are going to be the same. They are going to be 1 in each case, right? So this is the theorem 9.7, which is telling us that the determinant of A equals minus 1 or positive 1. Okay, so this is the theorem that we should keep in our mind. Okay, now let's go to the something else related to the usage of orthogonal matrices, that is when we can use it. Okay, when we can use it. For example, if we're talking about the eigenvalues and eigenvectors and so on, are we going to use it, or is it going to be useful for us to use the orthogonal matrices? Okay, let's read. Suppose S is a real symmetric n by n matrix with n distinct eigenvalues. Okay, so we have n distinct eigenvalues for this real symmetric matrix. Divide each eigenvector by its length. Length here means magnitude of the vector. Okay, if we have a vector 0, 1, 2, for example, the magnitude of this vector is going to be the length. We call it the length of this vector is going to be, let's assume it like this, for example, equals to square root of 0 squared plus 1 squared plus 2 squared. Okay, this is the magnitude or the length. We call it the magnitude or the length of the vector. Okay, so if we have the eigenvector, we are going to divide each eigenvector by its length or the magnitude and use these unit eigenvectors. We call this unit vector. Okay, the unit vector is, this is the unit vector. A unit vector is a vector with magnitude of 1. To find a unit vector u in the same direction of a vector v, we divide the vector by its magnitude. So if we want to get the unit vector u, it equals to the vector over its magnitude or the length. So 1 over the magnitude times the vector itself. So what is the magnitude? How we can obtain it? Here, for a vector v, for example, or nu, let's assume it's v, equals to a and b, which are the elements of this vector. Its magnitude is given by, as you can see here, as I said and mentioned here. So now we understood what is the meaning of this, that the eigenvectors are going to be divided by its magnitude or length, and use these unit eigenvectors as columns of an orthogonal matrix Q. We are going to use it as orthogonal matrix Q that diagonalizes S. So if we have this S again and it has eigenvectors, we are going to use the unit eigenvectors by dividing each eigenvector by its length or magnitude and use these unit eigenvectors as columns for a new matrix called Q. This Q diagonalizes S. Okay, so that's the issue. Theorem 9.9, an n by n real symmetric matrix is distinct with distinct eigenvalues. Look to here, distinct eigenvalues, okay, can be diagonalized by an orthogonal matrix. Can be diagonalized by an orthogonal matrix. Okay, so we need to have the orthogonal matrix based on the distinct eigenvalues and eigenvectors, but we are going to arrange the orthogonal matrix based on the columns of the of the orthogonal matrix is going to be unit eigenvectors of the original matrix that we have. Okay, now I think that we are waiting for an example to show what we are talking about is all, or what we are talking about can be applied or can be understood. Let's have this example. Let's assume that we have S, which is having this these elements, and let's assume that it's going to be real, as we can see here. It's real numbers. Symmetric matrix. It is symmetric. Has eigenvalues of 2, -1, and 4. So they are like 3 distinct eigenvalues with corresponding eigenvectors. So this is the corresponding eigenvectors: 0, 1, 0, 1, 0, 2, 2, 0, -1. Okay, so these are the eigenvectors of this matrix. Okay, now we are going to form a matrix called Q. This Q should always have the columns that is unit eigenvectors of the original matrix. So here we have the first eigenvector is 0, 1, 0. What is the magnitude of it? What is the length? 0, 1, 0. The magnitude is, as you can see here, 0 squared plus 1 squared plus 0 squared equal to 1. So the unit, this vector, or this unit, actually this eigenvector is unit vector because its magnitude is 1. Okay, what about the second and the third eigenvectors? Let's get their magnitude. 1, 0, 2. So we're going to find that the magnitude is square root of 5, and the third eigenvector, the magnitude is the radical of 5, or the square root of 5. What is the meaning of this? This means that the second and the third, they are not unit eigenvectors. We need to change them to eigenvectors, unit eigenvectors. So we are going to say this one, this second eigenvector is going to be 1 over square root of 5, and the same 0, and then 2 over square root of 5. This is going to be the eigen, or the unit eigenvector, the unit eigenvector. And the same for the third eigenvector, we are going to divide by its magnitude, which is the radical of 5. So it is going to be 2 over square root of 5, 0, and -1 over the square root of 5. Okay, so this is considered to be unit eigenvectors. So we are going to use them here. The first is the same. The second is going to be exactly as we have done before, making it unit eigenvector, and the third eigenvector is going to be changed or transformed to unit eigenvector and put it here. Okay, this Q with these matrices, let's clean here everything. This Q with unit eigenvectors as columns, we call that this Q is going to diagonalize S. Diagonalize S. What is the meaning of diagonalization? It is going to transform this real symmetric matrix to a diagonal matrix that is going to be easier to handle. Okay? So the matrix having these eigenvectors as columns will diagonalize S, as we said, but it is not an orthogonal matrix because these eigenvectors do not all have length 1. That's right. We said that this has the length 1, but this eigenvector and this one does not, or they do not. Normalize the second and the third, as we said, eigenvectors by dividing them by their lengths, and then use these unit eigenvectors as columns of an orthogonal matrix Q, as we have done here. This orthogonal matrix also diagonalizes S, as we said. Okay, so this is the interpretation of what we have explained here, that if we have S and we want a diagonal matrix or a matrix that diagonalizes S, we call it Q for example, then simply we are going to obtain the unit vector eigenvectors of this matrix and put it in a Q in a form of a matrix. The columns of the matrix are going to be unit vectors, and then this matrix we assume that it diagonalizes S. Okay, we assume that. Okay, the point here is these are what we call it unit eigen vector. They are not unit vectors only, eigenvectors only. They are unit eigenvector. What is the meaning of unit eigenvector? As we have mentioned here, that we need to divide the vector by its magnitude. How to obtain the magnitude? It is the radical of square root, the radical or the square root of sum of squares of its elements. Okay, so I hope that we have understood now what is the meaning, what is the meaning of the orthogonal matrix. Okay, this is the end of this video, and I'm going to explain another type of orthogonal or another type of special type of matrices in the next video, which is the quadratic form. Thank you, and see you in the next video.